Hello everybody, welcome to the Institute. Today's problem we're going to look at, this is kind of a crazy one. A loaded penguin sled is weighing 80 newtons and it's resting on a plane inclined at 20.2 degrees, and it wants to know what's the least magnitude parallel to the plane that will prevent it from slipping? What's the minimum magnitude that will start the sled moving up the plane? And what value is required to move the sled up the plane at a constant velocity? So it's three things kind of going on. So the first thing we really need to do is draw a free body diagram for this. So, like I've been doing, I'm actually going to start us off by not writing the weight, but actually writing the perpendicular forces here. So I'm going to have F perpendicular acting this way, and I would have an F parallel acting this way. And we know how to calculate those because we have those equations. And then in this particular case, we also are going to have a force up the incline. And then since they mentioned about friction here, both static and kinetic, we're also going to have some friction acting. So I'm going to keep that in mind. The other one we're going to have would be a normal force. Normal force is going to act this way. Since the force we're applying is actually, how does it say? Force parallel to the plane, the normal force will just equal our perpendicular force. So these will actually be equal in magnitude. They'll just be opposite in direction, so we don't really have to worry about them as much. So let's start with A. What's the least magnitude of the force parallel to the plane that will prevent the sled from slipping down the plane? So the least magnitude of the force parallel to the plane would be applying a force that would balance out the parallel force. So the idea of this particular problem is if I could apply this force over here, right there, to balance out my parallel force, then it would keep it from sliding. Okay? Now, that seems like a good idea, except I'm going to ignore that force for just a second and point out that there would be one more force in part A. So I'm going to end up erasing some of this stuff, but this is for part A right now. So in part A, I also have, besides my force, I would actually have friction acting in this direction. A little bit of static friction, because I'm going to try to keep it from actually prevent it from slipping down. So we're not going to have it moving. So static friction itself, I'm assuming, is going to be smaller than the parallel force, but when I'm trying to find this force for part A, let's start off with part A here. When I'm trying to find this force, it added with the little bit of static friction should equal my parallel force. So what we're going to try to solve for is F. So actually what I'm going to end up doing is I'm going to be taking the parallel force and subtracting the static friction. So the force I have to apply, the minimum force I have to apply, is enough to help out static friction and keep this thing from sliding. So that'd be the first part. We know how to calculate all of this. This would be mg times sine theta. And then my friction here would be mu s times mg cosine theta. And the reason why I get to use the mg cosine theta is because my perpendicular force is the same as the normal force, and that's how we find the perpendicular force. We find it with mg cosine theta. So that's where this kind of slips in there. So this is really, it's really the fun equation. It's really mu s times the normal force, but that's a way to kind of do it. So that's part A. I'll let you kind of do all the calculation. Part B is a little bit different. It says, what's the minimum force that will start the sled moving up the plane? So here's what happens when that occurs. Originally, friction here is helping me out, but when I start pulling it and I actually want to move it up the plane, what's going to happen is friction is no longer going to be acting in that direction. Now friction is always opposing the attempted motion. Now friction is going to suddenly be acting in this direction. Oops, gotta get my pin back. So now friction is going to be acting in this direction. And it's going to be static because I want to start the sled moving. So here's basically what's happening is now my force is going to equal the sum of those two. So it looks almost the same as what I just did here in part A, but now it's actually going to be equal to the sum of the two things because they're both acting against that force. And the numbers are actually going to be the same. So mg sine theta, mu s, mg cosine theta, we're all good. Now realize we have mg. This little 80 newtons right here, if I can get it, this 80 newtons right there, that is mg. That's the weight of it. So you can divide it by 9.8 and then multiply by 9.8, like divide it to get the mass and then plug it in. But I would just plug it in as mg and you should be good. So that's kind of the only difference between A and B. Now we come to part C. What value is required to move the sled up the plane at a constant velocity? So if I pull hard enough and I start it moving, then I'm overcoming static friction. Pretty much the only thing different in part C is now instead of having static friction here, we're going to have kinetic friction. So it's basically done exactly the same way, except that now we're going to switch from using our coefficient of static friction to our coefficient of kinetic friction for part C. So the idea, just like when you pulled the box on the horizontal surface when you did the friction lab, you had to overcome static. Once you did that, that tended to be your maximum. Then it moved at a fairly constant speed, and it dropped a little bit for you to become your kinetic. That's what you should have noticed. So that's kind of what's happening in this one. So kind of very similar setup. I thought this was kind of funny, and then the picture was just funny with the penguin. So hope you enjoyed.